In late 2024, astronomers using the Very Large Telescope Interferometer in Chile captured something that had never been seen before, the first detailed resolved image of the surface of a star called WOH G64, sitting roughly 160,000 light-years away in a neighboring galaxy known as the Large Magellanic Cloud. What they found wasn't just a distant pinprick of light. It was a star actively dying in front of their instruments, a red hypergiant so unstable that its own thermonuclear fusion had lost control, violently shedding its outer layers and wrapping itself in a dense, elongated cocoon of its own ejected material, like a body shedding its own skin under the pressure of its internal radiation. And the numbers behind that image are almost impossible to process. WOH G64 has a radius of roughly 1,440 times that of our Sun, which works out to about 665 million miles. If you swapped it in for our Sun at the center of the solar system, its outer surface wouldn't just reach past Earth. It would swallow Mercury, Venus, Earth, and Mars whole and keep expanding until it very nearly touched the orbit of Jupiter. Despite shining some 450,000 times brighter than our own star, WOH G64 is in a state of terminal collapse, losing millions of tons of mass every single second as it races toward a final catastrophic ending. When its core finally runs dry, the resulting explosion will be so powerful that, for several weeks, it will outshine every other star in its entire host galaxy combined, a supernova blinding enough to eclipse billions of suns at once before gravity finally wins and crushes what remains into a black hole. And here's the part that should really put things into perspective before we go any further. As monstrous as WOH G64 is, it isn't even close to the biggest thing out there. It's barely a starting point. Once you begin climbing the actual ladder of the universe's largest known stars, WOH G64 starts to look almost ordinary, dwarfed again and again by objects so large that human brains genuinely struggle to hold their scale in mind. So let's take that climb together, starting small and ending with an object that sits right at the theoretical edge of what a star can even be before the laws of physics say it simply can't exist anymore. We'll start with something familiar, because it helps to have a reference point before things get truly absurd. Vega, one of the brightest and most recognizable stars in the entire night sky, sits about 25 light-years from Earth in the constellation Lyra, and at first glance, it looks like a picture of stability. But even Vega makes clear just how quickly our own sun loses its status as anything special. Vega's radius comes in at around 1.2 million miles, roughly 2.8 times larger than the Sun. Drop it into the center of our solar system and it wouldn't just brush past Mercury, it would swallow it outright, while its intense radiation output would scorch every trace of life off Earth's surface almost instantly. Vega carries about twice the mass of our Sun, spins at a blistering 147 miles per second, fast enough to visibly flatten it at the poles into an oblate shape, and its surface burns at around 9,600 degrees Celsius, pumping out roughly 40 times more energy than our own star manages. It's an impressive, genuinely extreme object by any normal human standard. And yet, next to what's coming, Vega barely registers as a warm-up act. Moving into the constellation Gemini, we find Pollux, its brightest star, sitting about 34 light-years from Earth. Pollux belongs to an entirely different weight class than Vega. With a radius of roughly 4.3 million miles, this orange giant is nearly 3 times larger than Vega, and around 9 times the radius of our Sun. Swap it in for the Sun, and the entire inner ring of rocky planets, Mercury, Venus, Earth, and Mars, would be reduced to molten rock almost instantly. Despite running cooler than our Sun, its sheer surface area means it still radiates about 43 times more total energy. Pollux has already burned through the hydrogen fuel in its core and has begun the slow transformation into a loose, sprawling ball of gas, trading density for sheer volume in a process that's a defining feature of stars entering the later stages of their lives. But even this orange giant is little more than a shadow compared to what's next. In the constellation Taurus sits Aldebaran, sometimes nicknamed the Bullseye, a star almost 5 times larger than Pollux, with a radius stretching to roughly 44 times that of the Sun. Placed where our Sun sits, Aldebaran's outer surface would extend almost halfway to Mercury's orbit, instantly sterilizing the inner solar system with radiation before anything even had a chance to burn. Its photosphere runs at a comparatively cool 3,637 degrees Celsius, giving it that distinctive deep reddish glow, while its sheer size still makes it about 425 times brighter than our Sun. Aldebaran is also constantly shedding material, driving a powerful stellar wind that carries pieces of the star itself outward into space. There's a strangely poetic detail attached to this particular star, too. NASA's Pioneer 10 probe, launched all the way back in 1972, happens to be drifting on a trajectory that will eventually carry it toward Aldebaran's general direction. though nobody involved in that mission will ever know how the story ends, since the probe won't actually arrive anywhere near the star system for roughly another 2 million years. Aldebaran has already exhausted the hydrogen in its core and is expanding as it prepares to eventually shed its outer layers entirely, a slow transformation that will ultimately leave behind a white dwarf wrapped in a glowing shell of expelled gas. From here, we jump into an entirely different category of star. In the constellation, Orion sits Rigel, a blue supergiant roughly 860 light-years from Earth. Its radius comes in at about 33.7 million miles, which is 78 times the size of our Sun, nearly double the scale of Aldebaran in raw linear terms. If Rigel replaced our Sun, its gravity alone, combined with its ferocious output of ultraviolet radiation, would obliterate every trace of life on Earth almost instantly. Seen from our planet's surface, a star that size would dominate an enormous stretch of the sky, nearly a full quarter of the horizon-to-horizon view. What makes Rigel especially remarkable, though, isn't just its size. Unlike the bloated, low-density giants we've looked at so far, Rigel packs a genuinely massive amount of matter into that volume, roughly 21 times the mass of our Sun. Its surface temperature runs at a blistering 11,700 degrees Celsius, which translates into a luminosity around 120,000 times greater than our Sun's. Rigel represents a different flavor of stellar extreme, one where enormous brightness and enormous physical size arrive together, and it makes for a fitting gateway into the far stranger hypergiants that come next. Hidden behind a thick veil of galactic dust near the center of the Milky Way sits the Pistol Star, a blue hypergiant roughly 25,000 light-years away, buried inside the dense and chaotic quintuplet cluster. If Rigel's 78 solar radii seemed hard to wrap your head around, the Pistol Star blows past that scale by nearly 4 times over, with a physical radius of about 130 million miles, or roughly 300 times the size of our Sun. What truly sets this star apart, though, is its brightness. Current estimates put the Pistol Star at somewhere around 1.6 million times brighter than our Sun, with some data suggesting the true figure could run as high as 10 million times brighter. Placed at the center of our solar system, its scorching outer atmosphere would swallow the orbit of Mars whole, bathing everything nearby in lethal radiation. Every second, the Pistol Star sheds enormous quantities of its own mass into space, building an expanding nebula around itself as it slowly tears itself apart. From here on, though, it's worth setting aside the idea of stars that are merely dozens or a few hundred times larger than our Sun, because what comes next operates on a completely different scale of existence. In the upper shoulder of the constellation, Orion sits Betelgeuse, a red supergiant almost 2.5 times larger than the Pistol Star. Its radius reaches an almost unfathomable 330 million miles, roughly 760 times the size of our Sun. Swap the Sun for Betelgeuse, and its outer boundary would swallow the asteroid belt whole, reducing the entire inner solar system to scorched, lifeless rock. Betelgeuse's surface constantly pulsates with streams of unstable, superheated plasma, a sign that the star is preparing for its final act. And here's a genuinely unsettling twist. Some scientists believe Betelgeuse may have already exploded hundreds of years ago, and because of the sheer distance involved, the light from that explosion simply hasn't reached Earth yet. If that's true, the announcement of its death could already be racing toward us through the darkness of space at this very moment, arriving without warning at some unknown point in the future. When that light finally does arrive, the resulting supernova will briefly outshine the full moon in our night sky, turning night into something resembling day for several weeks. Beneath that brief, blinding spectacle, though, lies an inevitable and much darker outcome. All of that colossal volume of gas eventually collapsing inward under its own gravity, compressing hundreds of millions of miles of stellar material into an ultra-dense sphere only about 20 miles across, a black hole. It's the first point on this entire list where matter definitively loses its battle against gravity. Deep within the constellation Cepheus sits another pulsating giant, VV Cephei A, with a radius of roughly 454 million miles, or about 1,050 times the size of our Sun, comfortably surpassing even Betelgeuse. If placed at the center of our solar system, its diffuse, sprawling surface would swallow Jupiter's orbit whole, incinerating everything closer in. What makes VV Cephei A particularly interesting is that it isn't alone. It exists in a binary system alongside a smaller, extremely active blue companion star. And because gravity on the surface of a star this enormous is so weak, superheated gas is constantly siphoned off its outer layers and pulled toward its smaller neighbor, wrapping the whole system in a vast, glowing cloud of escaping plasma. It's a vivid illustration of a pattern that keeps repeating as stars grow larger. Matter trading density for sheer volume, becoming looser and less stable, barely held together by gravity that's simply too weak to contain it. Mu Cephei, sitting nearby in the very same constellation, pushes that pattern even further, setting a new benchmark among everything we've covered so far, with a radius of about 544 million miles, roughly 1,260 times that of our Sun. Positioned where our Sun sits, its outer atmosphere would stretch well past Jupiter's orbit, almost reaching the rings of Saturn. Its deep red color comes from an unusually low surface temperature of around 3,400 degrees Celsius, nearly 40% cooler than our own Sun's surface, and cooler stars tend to shift their light output toward the red end of the spectrum. Despite that lower temperature, Cephei's enormous surface area still makes it roughly 350,000 times more luminous than our Sun, and it remains one of the most recognizable objects in the northern night sky, constantly pulsating and shedding enormous clouds of dust that will one day become the raw building material for entirely new worlds. Even a giant like Cephei eventually loses out to VY Canis Majoris, a red hypergiant sitting roughly 3,900 light-years away in the constellation Canis Major. It edges past Cephei by roughly 13%, reaching a radius of about 1,420 solar radii, or around 613 million miles. Take the Sun's place with this star, and its surface would fully engulf Jupiter and press outward towards Saturn's orbit, turning the entire inner solar system into ash. Its photosphere runs at around 3,217 degrees Celsius, giving it a dim, smoldering red glow. And while our own Sun is expected to remain stable for roughly 10 billion years, VY Canis Majoris will burn through its remaining fuel in a mere 10 million years, an almost unbelievably short lifespan given its size. What's especially remarkable is the sheer scale of material it's shedding every single year, an amount of mass equivalent to roughly 30 Earths, blown outward in complex looping arcs that give the star the appearance, from a distance, of a glowing flower blooming in the emptiness of space. From here, the numbers stop climbing gradually and start compressing into a tight cluster of near record breakers. Deep in the heart of the Milky Way sits a cluster called RSGC1, home to no fewer than 14 red supergiants packed into a surprisingly small region of space. The largest of them, designated RSGC1F01, carries a radius of roughly 1,530 solar radii, about 660 million miles, enough to swallow Jupiter and reach towards Saturn's orbit if it replaced our Sun. Its surface runs at around 3,227 degrees Celsius, casting a deep red glow that manages to punch through the thick interstellar dust surrounding the cluster. Because of its unusually low mass relative to its enormous size, this star has only a few million years left before it collapses in a violent final explosion, and researchers studying the region have found that this particular cluster holds one of the densest concentrations of stellar matter anywhere in the galaxy. Moving out toward the edges of Cepheus, we find an object that has genuinely forced astronomers to reconsider some of their assumptions about stellar evolution. RW Cephei, roughly 11,500 light-years from Earth, edges out RSGC1F01 by a razor-thin margin of just 0.3%, reaching a radius of about 1,535 solar radii, or 667 million miles across. To put that scale into perspective, light takes only about 14.5 seconds to circle our own Sun, but circling RW Cephei at the same speed would take more than an hour and a half. Its surface temperature sits at around 3,194 degrees Celsius, casting a menacing red tone across the surrounding darkness. In 2022, RW Cephei genuinely shocked astronomers by suddenly dimming, ejecting an enormous cloud of material into space that formed a thick, opaque dust shield around itself, expelling an amount of matter comparable to the combined mass of several planetary systems in one event. It isn't a stable ball of gas at all anymore, but a chaotic, pulsating mass actively losing its own coherence in real time. Just as absurd, and located at that same rough distance of 11,500 light-years, is Westerlund 126, a red supergiant that edges past RW Cephei by roughly 3%, with a radius of about 1,980 solar radii, or 682 million miles. Swap it in for the Sun, and its outer atmosphere would immediately swallow Jupiter and reach as far as Saturn. Its photosphere has cooled to around 2,527 degrees Celsius, roughly half the surface temperature of our own Sun, giving it a deep, dull glow among its neighboring stars. Outer layers only detectable through the dense curtain of stardust surrounding it. It's in the final stretch of its active life, with only a few million years remaining, and much of what astronomers know about it comes specifically from radio wavelength observations, which reveal that Westerlund 1-26 is wrapped in a vast nebula of ionized gas, the visible remnant of powerful plasma ejections from its glowing. That brings us to UY Scuti, a red supergiant roughly 9,500 light-years away in the constellation Scutum, and for years this was considered the single largest known star in the entire universe. UY Scuti surpasses Westerlund 1-26 by about 8%, reaching a radius of roughly 1,708 solar radii, or 738 million miles, large enough to contain nearly 5 billion suns within its volume. Here's a way to actually feel that scale. If you shrank our own sun down to the size of a tennis ball, UY Scuti, at the same proportional scale, would balloon out to a sphere roughly 374 feet across, longer than a football field and taller than a 40-story building. Positioned at the center of our solar system, it would fully swallow Jupiter's orbit, with its outer atmosphere reaching all the way to Saturn. Its surface temperature sits at a relatively cool 3,092 degrees Celsius, and yet it still shines about 340,000 times brighter than our sun. Given the extreme rate at which it's burning through helium in its core, UY Scuti has only a few million years left before its own ending. The star has no clearly defined edge at all. Its gravity is so weak relative to its size that its outer layers are constantly bleeding off into space, wrapping it in a dense haze of scorching dust, and its measured size and brightness genuinely fluctuate on a 740-day pulsation cycle. Here's the strangest detail of all. Despite being 708 times larger and 340,000 times brighter than our sun, UY Scuti's actual mass is only about 10 times greater, a staggering imbalance between raw size and raw substance. And now we arrive at the current record holder, an object so large it seems to defy logic. Roughly 20,000 light-years away, inside the Stephenson 2 cluster in the constellation Scutum, sits Stephenson 2-18, widely regarded as the largest known star in the observable universe. It surpasses UY Scuti by about 26%, with a radius of roughly 2,150 solar radii, or 929 million miles, large enough to swallow 10 billion suns inside its volume. Placed at the center of our solar system, it wouldn't just engulf Jupiter and Saturn. Its outer surface would extend all the way to the boundary of Uranus's orbit, turning the entire inner and mid-region of the solar system into a superheated wasteland of plasma, erasing any physical trace that planets had ever existed there. The scale here is genuinely difficult to translate into anything resembling a normal human comparison. A beam of light, fast enough to circle the Earth 7 times in a single second, would still need roughly 9 hours just to complete one full loop around Stephenson 2-18's equator. If you sent an ordinary passenger airliner, cruising at around 560 miles per hour, on a trip around the star's circumference instead, that single journey would take more than 130 years to complete, long enough that dozens of generations of crew members would need to hand the controls down to their descendants before the trip was finished. Its surface has cooled to roughly 2,127 degrees Celsius, giving it a deep red hue typical of these enormous, unstable bodies teetering on the edge of thermal stability, and its total luminosity is estimated at around 440,000 times that of our sun. At the star's outer edges, the density of matter drops to levels millions of times lower than the density of Earth's own atmosphere, meaning Stephenson 2-18 isn't really a solid, cohesive sphere at all in any conventional sense, but an enormous, loosely bound cloud of superheated gas held together only by the faint remaining pull of its own weakening gravity. Astronomers believe Stephenson 2-18 sits right at what's known as the Hayashi limit, a theoretical boundary beyond which a star simply cannot expand any further without breaking down entirely, making it not just the largest star currently known, but very possibly somewhere close to the largest a star can physically be at all. Remarkably, there are 26 other red supergiants sharing that same cluster, and not a single one of them comes anywhere close to matching it. Because of its enormous size and comparatively low mass, Stephenson 2-18 has only a few 100,000 years left in this form before it detonates in an extraordinarily powerful hypernova, an explosion bright enough to briefly outshine much of its host galaxy. What's left behind afterward will be a massive black hole, an object that will spend trillions of years silently consuming any light or matter unlucky enough to drift too close. The final, quiet ending for a star that, for one brief and almost incomprehensible stretch of cosmic time, represented the absolute upper limit of how large a single star in our universe could ever become.